This is the second video in our series on chemical equilibrium. And what we've done in the prior video is examine what happens for simple reaction, an isomerization process in which A turns into B. And we have examined what happens when you reach the point of equilibrium in that reaction. Okay, so the conclusion is that at equilibrium, the value of the reaction Gibbs energy will be 0. And then we have that the reaction quotient is what we know as the equilibrium constant. Okay, so we can rewrite that expression simply as 0 is equal to the reaction Gibbs energy at the standard state plus RT natural log of the equilibrium constant. Okay, what we do in this video is try to examine a little bit more closely the relationship between the equilibrium constant and the reaction Gibbs energy at the standard state and see what can we learn from that. All right, the reaction Gibbs energy at the standard state is then going to be equal to minus RT natural log of the equilibrium constant. And if we solve for the equilibrium constant, we get to an expression where you have E to the minus reaction Gibbs energy at the standard state divided over RT. Okay, now this is extremely useful because you have a direct relationship between the equilibrium constant, which is a very, very powerful and very useful quantity in chemistry, okay, with the reaction Gibbs energy at the standard state. Now it turns out that this reaction Gibbs energy at the standard state is something that we have dealt with in the past. Okay, we learned how to calculate this from the reaction enthalpy at the standard state and for the reaction entropy at the standard state. These are all quantities that appear in the first law of thermodynamics, in the second law of thermodynamics, so we actually have a very good training in calculating them and then putting together to calculate the reaction Gibbs energy. This value can be calculated from standard enthalpies of formation that come in tables. This value can be calculated from standard molar entropies that also come in tables. So again, we've used a few examples to calculate what this reaction Gibbs energy at the standard state is. And again, it turns out that you can then directly relate that value that is simple to calculate with the equilibrium constant, which again is a pervasive concept in chemistry and is a very powerful quantity. So let's run here a numerical example to see exactly how this is done. The reaction that we're going to be focusing on is one of interest in the life sciences. It will be the isomerization of glucose 6-phosphate over fructose 6-phosphate. And our goal here is to try to calculate the equilibrium constant for that process and what it means from the value of the reaction Gibbs energy at the standard state, which in this case we could calculate using this recipe from tables, or it can be given in the statement of a problem, and it is. Okay, so again, the statement of the problem would be try to calculate the equilibrium constant from the reaction Gibbs energy at the standard state of that reaction, which happens to be equal to plus 1.7 kilojoules per mole at 298 Kelvin. Right, so our equilibrium constant will also be at 298 Kelvin. All right, so let's plug in some numbers and see what we learn from them. The equilibrium constant then is going to be equal to E to the minus 1.7 10 to the 3 joules per mole divided over R, 8.314 joules per mole Kelvin, times the temperature, 288 Kelvin. Okay. All of the units cancel, and then you get that the value of the equilibrium constant is 0.50. And again, notice that the equilibrium constant, much as the reaction quotient, is dimensionless for any chemical reaction, regardless of whether you have one reagent on one product or any number of reagents and products, whether those are gases. Again, the equilibrium constant and the reaction quotient, Q, they're always dimensionless. Now the question is, well, what type of information do we learn from this value of Q, of K, the equilibrium constant? What is that telling us? Right, this equilibrium constant is telling us the following. Suppose that we were able to map here how the concentrations of glucose 6-phosphate and fructose 6-phosphate change in time. Now, if the reaction went to completion, okay, your glucose 6-phosphate, which will be this line, okay, will undergo a change like this. Okay, it will decrease with time, until it eventually fully disappears. And the concentration of fructose 6-phosphate, which will be right here, will start from 0 if you don't have any fructose to start with, and then it would only increase until you get to that point. And this will be for 100% completion. But this is actually something that does not happen in this particular case, because this equilibrium constant, you can notice that is going to be equal to the concentration of products, fructose 6-phosphate at equilibrium, over 1 molar, over the concentration of glucose 6-phosphate at equilibrium over 1 molar. We can simplify this a little bit by erasing these 1 molar concentrations. Just cancel each other out. And then you have that the equilibrium constant is simply the ratio of those two. And this value has to be equal to 0.50. Okay, so if you didn't have any, or not a very small amount of glucose 6-phosphate left, and a large amount of fructose 6-phosphate form, then the equilibrium constant will not be that number, it will be a much greater number. Okay, the fact that this is 0.50 is telling you that you actually have twice as much glucose 6-phosphate at equilibrium than you do of product, fructose 6-phosphate. So that graph does not look like what we have drawn here. Instead, it actually looks like this. You will have that after you have decreased by about a third, okay, of the concentration, then you reach equilibrium. Okay, and then the concentration of fructose 6-phosphate is only a third of the maximum that you would have. Right? So notice that the concentration of glucose 6-phosphate has to be twice as large as that of fructose 6-phosphate. Okay, so that is kind of the interesting aspect of the equilibrium constant. You can see how displaced the reaction is towards products. And for this particular case, we actually find that the reaction is not heavily displaced towards products, right? You've only gone about a third of the way, or 33% completion. Okay, again, that's the power conveyed in the equilibrium constant. Now we can generalize these findings of the relationship between the equilibrium constant and the reaction Gibbs energy by noticing that the sign of the reaction Gibbs energy tells you about whether you're displaced towards reagents or towards products. If this number is positive, like what we have right here, okay, then it turns out that the equilibrium constant is less than 1, and the reaction is not displaced towards products. It's actually going to stop before you get to 50% completion. Okay? If the reaction Gibbs energy at the standard state happens to be negative, okay, then the equilibrium constant will be larger than 1, and then we say that the reaction is displaced towards products because you can convert more than 50% of reagents into products. Okay, the medium point would be when the reaction Gibbs energy at the standard state is 0. That will mean that the equilibrium constant is 1, and then you have exactly the same amount of reagents and products at equilibrium. Okay, so notice how beautiful and simple this is, right? Just the sign of the reaction Gibbs energy at the standard state, which is something that we know how to calculate, informs where the point of equilibrium is in a particular chemical reaction, whether that is heavily displaced towards reagents, or towards products, or more towards reagents, or whether it's in an intermediate point. Okay, so again, this is just a summary of what we've been trying to do here with the concept of chemical equilibrium. Okay, notice that the chemical equilibrium constant is related to reaction Gibbs energy according to this equation, and that's the knowledge that you can get from there.